Okay, hi. So this is going to be the second part of our chapter, and in this part we will discuss Gauss's method. Gauss's method, and I will divide this part into two. Okay, into two videos. I want to say in the first video is going to be the lecture, the more theoretical part, and then in the second video we will do the tutorial. Okay, so bear with me if in this video we do more um, definitions, more theories. Okay, but we will do some tutorials to illustrate the concept we will see in this video. Okay, so let me start with number one, the introduction. Before we dive into Gauss's method, let's see why we are even doing Gauss's method. Okay, introduction. As I said earlier, the main purpose of studying linear systems of equations is to find the solutions. So roughly everything we are going to discuss in this chapter is about the solution sets of a linear equation or linear systems of equations. Okay, so let's ask ourselves the following question: how to solve a linear system of equation? Okay, how to solve a linear system of equations. How are we going to do that? And the answer is we have two methods. Okay, we have two methods. Method one is Gauss's method. So you see, now you see why we are doing Gauss's method. Okay, so first of all, we perform Gauss's method to bring the linear system, okay, into its echelon form. We will see shortly what we mean by echelon form. Okay, then we do back substitution. Okay, that's how we solve linear systems of equation. The first method, the main one actually, the most used method is the first is this method, Gauss plus back substitution. But later on in this chapter, we will see a second method, okay, called, this method has only one part, okay, that's its advantage. This method is called Gauss-Jordan. It's called Gauss-Jordan, okay, method or reductions. And this helps us to bring the linear system to the reduced, okay, echelon form. So that's the two methods we can use to solve linear systems of equation, actually in our lecture series, in this lecture series, of course. We have other methods, but they are roughly the derivation of these two main methods. Okay, so that's the introduction. So this second part is about Gauss's method. So this is giving this introduction is to give a context to why we are doing Gauss's method, is to be able to solve linear systems of equation. Is that okay? So that's that one done. let me now talk about the Gauss method itself, the theorem. Choose the theorem about Gauss method. Theorem is called Gauss method. Okay. So Gauss method says the following. Okay, it says that as I said here, I said Gauss's method will allow us to have the linear system in the echelon form. That means we have the linear system in, first of all, in its original form, and then we will do some stuff to the original form to have a new form we are going to call echelon form. Is that okay? So basically, what the theorem says is when we have an original form to begin with, and we do some operations, those operations we are going to call them Gaussian operation, we will see it shortly. If we perform these operations to the original system, the theorem says that actually we are not changing the solution sets of the two systems, if you get me. So that's the logic behind it, because as I said, the main purpose why we are doing this chapter to begin with is to solve linear systems. So we are going to see ways to be able to find the solution sets to the system. So this theorem about Gauss method says that if we perform the following three main operations I will describe shortly to the original system, the solution set of the original and the newer form, which is the echelon form, the solution set of those two systems is the same. Okay, I'm sure it makes sense, because if performing Gauss's method to the original form and it changes the solution set, so why we are even doing Gauss's method if we are going to do an operation that will change the solution sets of the original system, if you get me. So that's the main purpose of Gauss's method. We will have original system, we will do some stuff to it to have the echelon form. The advantage of the echelon form is it will help us to decide or describe or find the solution of the original system. So if we perform the following three operations I'm going to describe shortly to the original system, we do not change the solution set. Is that okay? Okay, so now let me give the formal uh, theorem, the formal form of Gauss's method. Gauss's method. Okay, if a linear system of equations is changed to another system, of course, to another system by one of these operations, as I said. What are those three operations? They are: number one, I'm going to call it swapping. Okay, let me write it here. Swapping, and let me define it. What do we mean by swapping? Is when an equation is swapped or replaced by another one. So if an equation is swapped with another, okay, and the second operation is called rescaling, or multiplying by a scalar, or multiplying by a scalar. Okay, so let me define what we mean by rescaling. So basically, when an equation has both sides multiplied by a non-zero constant. Okay, so that's what we mean by rescaling. And the third operation is a row combination. So when we perform a row combination, and what do you mean by row combination? By row combination, we mean when an equation is replaced by the sum of itself and a multiple of another. Okay. Then, okay, so Gauss's method says if a linear system of equation is changed to another system by one of these three operations, then the two systems have the same set of solutions. Okay. Then the two systems have the same set of solutions. Okay, so this is our famous Gauss's method. If you don't really understand the theorem, don't worry. In the next video, we will do the tutorial and I will explain it to you, okay, with some examples. And I will also see what we mean by echelon form. Okay, so that's the let's continue with number 3 of this part is a definition. Let's see another definition. Let's see 3 definitions. Definitions is very important that we have a clear understanding of the terms we are going to use. So let's see these 3 definitions. The first one is okay, so we have seen the 3 operations. Let's see if I have enough space here. No, these 3 operations we have just discussed in Gauss's method, okay, they are known as elementary reduction operations or row operations or even Gaussian operations. Okay, these 3, the swapping, rescaling, and row combinations. So let me give a formal definition here. The 3 operations in Gauss's method. Okay. Okay, the theorem you have seen in Gauss's method. Okay, those three operations are known as either you can call them elementary reduction operations or row operations or Gaussian operations. Okay, and yeah, let's give another definition. Says in each row of the system, okay, the first variable is going to be called the leading variables. So this is also an important term, the term leading variable or important terms. Leading variables is important. Okay, so let me give a formal definition and then I will do a tutorial later on. In each row of a system, okay, the first variable, with a non-zero coefficient is known as the row's leading variable. Okay, and then as I said later, earlier on, Gauss's method is having an original system. Okay, so let me explain, then I will give the formal definition. Okay, so basically, let's say we have a linear system of equations like this. So we have equation 1, a11 x1 plus, blah blah blah, equals to d until we have a1 am1, okay, blah blah blah, x1 until, see, this d1, this is dn. This is our original system of equations. So basically we will perform Gauss's method. So we will do Gaussian operations, those three operations. So let me see, write it here, Gauss's method to this system to be able to have, so let me call it the original. This is the original system. And Gauss's method will help us to have a new system called echelon form. Okay, so basically what does echelon form look like is something like this. So we have our first equation will be like that, then the second equation will be something like this, the third. So if we speak French, I think the word echelon can mean something to you. It comes from the French word échelle, and when you have the word échelle in this context roughly means something like something that has to do with the stairs. Okay, so as you can see, this is our echelon form. So it's like you are going from one step to another to another. Okay, so it has the concept of a hierarchy. Okay, so yeah, basically when we say echelon form, you must have the following picture in mind. Okay, So let me now give you the formal definition of when a system is in echelon form. Okay, so a system is in echelon form if each leading variable is to the right of the leading variable in the row above it. Okay, except for the leading variable in the first row. In the first row. And any row with zero coefficient are at the bottom. Okay, so in the next lecture, I will explain. I will give an example, but let me give you again the picture. So let's say, for example, we have the following linear systems of. Okay, so let me write a1 x plus a2 y plus a3 z equals to d1. Okay, this is just an example to illustrate the echelon form. So here we have b1 x plus b2 y plus b3 z equals to d1, and c1 x plus c2 y plus c3 z equals to d3. Sorry, this is d2, d3. So basically we will do Gauss method or Gaussian operations. Okay, to be able to have something like this. So what we say is we want to have the echelon form. So let's pick the first equation here. It's leading variable, so here we'll assume that a1, so this is a1, okay, that a1 is non-zero. So the leading variable of the first equation is x. So we will repeat that first equation, okay, in the first row. A1, a2, y plus a3, z equals to d. Now we will use this, the term of the leading variable, okay, we will use the a1, x1 to eliminate these two, okay. So we have this first column, okay, so we are going to use the leading variable of row 1. We are going to use that leading variable to eliminate the same variable in that column. So in the row below, so row 1, so we have row 1, row 2. In row 2, row 3, we have to do stuff to be able to eliminate those two terms, those terms in X. So that's how we are going to use Gauss's method to eliminate those terms. So basically, our second equation must be something like, let me say, m1y plus m2 z equals to, so that's our d1, this is going to be dm. This is just an example, easy. So, and then what we have to do is at some stage, okay, so we have to use the term in the second, if we pick the second equation, the leading variable is in y. So we are going to use that term y to eliminate the term in y in the third equation somewhere here, to be able to have something like nz equals to dn. So as you can see, as our definition here, that's what I want to illustrate, that the definition says, so this is our echelon form, okay? Echelon form, okay? And as I said, it looks like this. Okay, so it looks something like this. It looks like, something hierarchical. So the definition here says a system is in echelon form if each leading variable, so the leading variable here in equation 1 is there, and the leading in equation 2 is m1y, and the leading variable in equation 1 is there. So as the definition says, the leading variable in each row is on the right. So here is the leading variable in equation 1, and here is the leading variable in equation 2, and the leading variable in equation 2 is on the right of the leading variable in equation 1. Okay, the same for the leading variable in equation 2, in equation 3 is to the right of the leading variable in equation 2. So a system is in echelon form if each leading variable is to the right of the leading variable in the row above it, except for the leading variable in the first row. Okay, so that's the first row is on its own. Okay, we are starting with that first, the leading variable of the first row, but the leading variable in the second row is to the right of the leading variable in the first row, and the leading variable in the third row is to the right of the leading variable in the second row. So that's how we get the echelon form, but the question is, how are we going to eliminate, those terms in the column of the leading variables, okay, below, okay, the leading variables in the first, in the same column. That's how we are going to apply Gauss's method in the next video. Is that okay? Okay, so in this video is just I'm just trying to explain the concept before we get into the tutorials, okay, to the applications. Otherwise, we may not be able to grasp, okay, the concepts. So the last concept of this video is the different types of solution set for a linear system of equation. Okay, so for I discuss the types of solutions for a linear system of equation. Okay, equations. So when it comes to linear systems of equations, we have three types of solution sets. Okay, and here I'm going to discuss those three types of solution set and how do we recognize them? How do we recognize if a linear system of uh, equations has those types of solutions? Number one, a linear system of equations can have no solution at all. And how do we know that? Thanks to echelon form, okay, thanks to Gauss's method. How do we know that? Is when you perform Gauss's method to the original system of equations, and when you arrive at the echelon form, you have a contradiction, you have contradictory equation, okay? That's when you know that the system has no solution, okay? So let me give the formal definition. When performing row operations or Gaussian operations or elementary reduction operations, row operations, there is a contradictory equation. There is a contradictory equation. That's when you have no solution. Basically, let's say you are doing Gaussian operation or row operations, and then at some stage you have something like 5 equals to minus 3. That's not true, right? So you have a contradictory um, uh, equation. So that means the linear system has no solution, okay? Number two, a linear system of equation can have a unique solution. This is what we love the most. Has a unique solution. So how do you know if a linear system has a unique solution? We have the following two things. Okay, number one, when you arrive at echelon form and there is no contradictory equation. That's the main thing to look for. And the second thing is that if each variable is a leading variable in its row. So when we have 3 equations with 3 unknowns, to be able to have a unique solution, first of all, we need to arrive at echelon form without a contradiction. And then number two, in echelon form, we need to have x leading the first row, y leading the second row, and z leading the third row. Okay, let me give the formal definition. If we arrive or we reach the echelon form without a contradictory equation, okay, and when each variable is a leading variable in its row. Okay, this is yeah, in its row. And lastly, a linear system of equation can have infinitely many solutions. Many solutions. And how do we know? if our linear system has infinitely many solutions, um, number one, we need to get to the echelon form without contradiction. Okay, that's the condition to have a solution to begin with. Now we need when it comes to infinitely many solutions, uh, we need to have at least one variable that doesn't lead a row. Okay, so that's when we know that we have infinitely many solutions. So first of all, if we reach the echelon form without a contradictory equation, and when there is at least one variable that is not a leading variable. Okay, if there is at least one variable that is not a leading variable. Okay, so I would like to stop the lecture here, and in the next video we will do the tutorial. Okay, so here in this video we discuss Gauss's method, where we have seen the two ways of solving a linear system of equations. We say we have the Gauss method and Gauss-Jordan's method. But in this video we discuss Gauss's method by seeing the three operations in the theorem about Gauss's method. Those three operations are swapping, rescaling, and row combinations. And then we have seen, few definitions about the three operations in Gauss method theorem. Those three operations are known as elementary reduction operations, row operation, or Gaussian operations. We have in this video we have also seen the definition of the concept leading variable is very important. Okay, and we have also seen the definition of an echelon form of system. Okay, and we have finished this lecture by discussing the three types of solutions of a linear system of equations. Those three types are, the linear system may have no solutions at all. The linear system can have a unique solution, and it can also have infinitely many solutions. Okay, so we will stop the definitions and the theories here, and in the next video we will do the tutorial, okay, to illustrate everything we have learned in this video. Okay, see you in the next video. Thank you.